All right, lecture 6A today will be to first discuss what I wanted to do at the end of lecture 5 last time, and that is what makes mod n, addition mod n arithmetic work. You know, it's sort of like, you sort of feel like you can throw the mods around it anywhere you want. And we'll look a little deeper into why that works. And that does include looking at a homework problem that we turned in last Wednesday that I didn't grade, because there's some subtleties in it that I want to go over, but there could be something that shows up on the exam. Review the order of a group and a group element, review the idea of a subgroup, and then we'll also talk about subgroup tests, and we'll do plenty of examples. I'll talk about plenty of examples as we go here. Lecture 6B, I'm sure the subgroup stuff will go into lecture 6B, so I'm setting more on subgroups. And in introduction to cyclic groups. Okay? So here is a slide with a little bit of taking a fancier, initially here this is sort of a fancier approach to modular arithmetic. What's really going on with modular arithmetic? Actually, that's a typo. Not for multiplication, but instead for addition. Two typos in a row here. Okay. I had a typo last Friday. In other words, what is mod n really about? In reality, it's really a function. For any fixed integer n, positive integer, we could use this kind of notation. We could write mod sub n as a function whose domain is the set of integers and whose codomain is the set of a finite set of integers from 0 through n minus 1. So the outputs are going to be integers 0 through n minus 1. Defined via the division algorithm as mod sub n of a equals r, where r is the unique, emphasis on the word unique there, unique integer in this set with this property, right? That's what the division algorithm says. A equals, we're dividing a by n times the quotient plus the remainder, where q and r are unique with respect to the property that r is greater than or equal to 0 and less than n. Right? That's what the division algorithm says. So with respect to the fact that r is unique, you can define this function. So it really is a function. Our notation doesn't really emphasize that it's a function, but it really is. You know, when you write 7 mod 5, for example, equals 2, according to this notation up here, you're really saying the function mod sub 5 applied to the input 7 gives you the output 2. What are the key properties from, again, typo, addition mod n to work? I better fix it right now, otherwise I'll forget. Maybe look at multiplication next time. Well, first of all, there's the exercise that I didn't grade, exercise 7. If a and b are integers and n is a positive integer, then a mod n equals b mod n if and only if, two directions to prove, n divides a minus b. In other words, the output of this function is the same for these two different inputs if and only if n divides a minus b. A and b can definitely be different numbers here. Okay? Let's go ahead and prove this carefully. Again, it's an if and only if, so that means you've got to prove two directions. Proof of exercise number 7 from chapter 0. And one of these directions is kind of subtle. It's got some subtleties. I looked at a few of your answers and nobody really that I saw paid attention to those subtleties, so I decided not to grade it. I was also low on time. One direction's fairly easy, the left to right direction. If you assume a mod n equals b mod n, if you assume they have the same remainder, when you divide by n, where the remainder is between 0 and n, then n divides a minus b. That's fairly easy. Let's go ahead and write this out carefully. Suppose a mod n equals b mod n, then by the division algorithm, there exists unique. Well, they could have different quotients when you divide them by n. It's the remainders that have to be the same. I'll go ahead and write Q1, Q2, and R in the integers such that A equals NQ1 plus R and B equals NQ2 plus R, with, again, R being between 0 and n. It could equal 0 but not equal n. It's unique with respect to that property, the uniqueness. That's with respect to this property right there. Now it's just a matter of subtracting and noticing that the r's cancel. It's the same r for both of them, because I'm assuming A mod n equals B mod n. Therefore, A minus B is NQ1 plus R minus, in parentheses, NQ2 plus R. Minus sign goes through the parentheses, the r's cancel. You can factor out the n with what's left. A minus B ultimately is n times, in parentheses, Q1 minus Q2. So n divides A minus B. Right? So that direction is not too difficult. It's the other direction that's a bit more difficult, it's a bit more subtle. And it's going to bring up an important point that you can sometimes do in proofs, something that you should pay attention to. So what's the other direction? I'm going to suppose n divides A minus B and show that the remainder I get when I divide A and B by n is the same with respect, again, to the condition that it's between 0 and n. Like that. So I can say, suppose n divides A minus B. I can go ahead and apply the division algorithm to this, but the remainder is going to be 0 because of this assumption. But let me go ahead and phrase it in terms of the division algorithm anyway. By the division algorithm, there exists unique, call them maybe capital Q and capital R, just to use some different notations, such that A minus B equals n times capital Q plus capital R, where capital R is between 0 and n, could equal 0 but cannot equal n. Again, the uniqueness is with respect to that property. And in fact, capital R equals 0 since n divides A minus B, but I wanted to write it anyway. I wanted to use the notation capital R. What's the goal here? Again, the goal is to show A mod n equals B mod n. When I divide A and B by n, I get quotients that could be different, but a remainder that's the same with respect to the property that is between 0 and n. By the division algorithm again, there exist Q1, Q2, R1, and R2. Use two different letters there, such that A equals NQ1 plus R1 and B equals NQ2 plus R2, with both R1 and R2 being between 0 and possibly equal to 0, but less than 10. Now here's the subtle part. Okay, many people, the few people that I looked at actually, went ahead and they So they had this kind of thing, and they subtracted a minus b, and they wrote an r1 minus r2 in what they had after doing that subtraction, and said, oh, r1 must equal r2 because that remainder must be 0. That's kind of right, but you really need to say something else first. See, the problem with that is r1 minus r2 could be negative. r2 could be bigger than r1. However, we can say something else. This is very common in proofs. Log. No, don't say log. Well, you can if you want. WLOG. Does anybody know what that stands for? Maybe you saw it in discrete math?
Without loss of generality.
Without loss of generality. She's had me before for proof classes. Without loss of generality, WLOG, we may assume R1 is greater than or equal to R2. Why may we assume that without loss of generality? Is that something that needs to be justified? Well, it should be at least in your mind. And you would hope the reader would believe that this is valid. Anybody want to give a reason why we can assume this? I mean, couldn't R2 be bigger than R1?
Is it because A and B are arbitrary, so one of them is going to have a bigger one, so it doesn't matter?
Yeah, A and B are just arbitrary symbols anyway. If R2 was bigger than R1, we just switch the roles around. So this is definitely something we can assume, and that is the subtlety that's important here. Now go ahead and subtract A minus B. A minus B is, if you do the algebra right away here, let me just write it in factored form right away, like that. And again, see, without saying without loss of generality, we may assume that it's conceivable this could be negative. And that would mean that it's not the remainder that would be guaranteed to be unique in the sense of having this thing true from the division algorithm. Say it again. R2 could have been bigger than R1 if I didn't say this. That could have been negative, which means it would not fit this inequality right there. And it does now, since I made the assumption. Again, this is greater than or equal to 0 by the assumption here. I guess I'm not doing perfect sentences here. You can write that out. So it fits this inequality for capital R. And by the way, this will be capital R. Does it fit that inequality? Is it less than n? I mean, couldn't R1 be a lot bigger than R2? Couldn't that be bigger than n? Well, no. There's constraints on how big R1 can be, right? It's less than n. We got it from the division algorithm. So this can't be too big, it has to be less than n. And R1 minus R2 is less than n. Since R1 is less than n, and R2 is not negative, we're not subtracting a negative number. Can you see over there? Zoom in if you need to. So this difference is between 0 and n. Greater than or equal to 0 and less than n. It's got to be capital R. Therefore, R1 minus R2 equals capital R, which we remarked above was 0. And therefore, we're done. Therefore, R1 equals R2. And that means A mod n equals B mod n. How about that? Is that too low? Okay. you guys? Let me see it. Stand up if you need to. Okay, so it's subtle. But it's an important thing to state to really make the proof airtight. What's another fact that makes modular arithmetic work? Really, exercise 7 is a gateway to proving exercise 9, which is really more important in terms of making the modular arithmetic work. If A mod n is A prime and B mod n is B prime, then you can find A plus B mod n by adding A prime and B prime, and then modding by n. In function notation, you can write it like that. A bit more complicated looking, isn't it? Why is this justifying addition mod n? Well, for example, it's justifying calculations like this. 17 plus 16, say mod 7. You could add the 17 and 16 first and then do mod 7. Or you could mod 7 first. 17 mod 7 is 3. 16 mod 7 is 2. The answer is 5. You can mod first, is the point. And in fact, you could theoretically mod over and over again before you do your final addition. I could have written mods in here as well. 3 mod 7 is 3. 2 mod 7 is 2. I could have written those mods in here too to match what you see, right? Well, okay, I guess I don't have them right next to those. I put the mod at the end. You can essentially throw the mods around anywhere you want, okay? It's kind of the confusing point at first, but this is essentially why it works. How do you prove this? Use number 7. We want to show that these two things, mod n, are the same. By number 7, that's going to be true if n divides their difference. I need to use this assumption that A prime and B prime are what A and B equal mod n. By the division algorithm again. A equals nq1 plus A prime, and B equals nq2 plus B prime. I guess I should say, I should have added, there exist q1 and q2. A prime and B prime are given to be equal to these things. With, once again, this being true and this being true. Now it's just a matter of doing the subtraction. Here's again the equation you want to show. We're pointing here. By number 7, I can show that if n divides this minus that. So do the subtraction. Then A minus B, nq1 plus A prime minus nq2 plus B prime is n in parentheses q1 minus q2 plus A prime minus B prime. Oops, mistake, sorry. That's the wrong subtraction to do. I want to do A plus B minus A prime plus B prime. That's what I want to do. Replace A and B with nq1 plus A prime and nq2 plus B prime. Distribute the minus sign through the parentheses in the second one. The A primes cancel, the B primes cancel. You're left with a multiple of n. And therefore, by number 7, since n divides this difference, it follows that this mod n and this mod n are the same. It's okay if I don't write that. You should say, therefore by number 7, this is true. And that will finish the proof. Okay, so essentially it's justifying that at least with addition mod n, you can sort of mod whenever you want to, is the idea. And that doesn't fully justify modding whenever you want to, but it's part of the way that you could say. Next time, maybe we'll look at multiplication modding. And hopefully I won't make typos. Hopefully I'll remember to change it. Those typos aren't there anymore. All right, reviewing definitions from last time. Going to go pretty quick through this. Order of a group and the order of elements, not too difficult of a concept. The order of a group, G, is the number of elements in G. If G is a finite group, if it's got finitely many elements, then that number, that cardinality, is an ordinary positive integer. 1, 2, 3, 4, 5, 6, etc. Our book uses this symbol for the order. Do not say absolute value. Okay, if you say absolute value accidentally, I might need to do something not so nice. I'm just kidding. It will make me upset. No. Don't say absolute value. Say order of G. Some books avoid that problem, avoid the professors getting mad by writing or G or even just OG. This is an O here, not a 0. O of G or G. It's not a perfect definition here, by the way. The book's definition is better. I'm just sort of using this as a pseudo definition. Because what does number of elements mean when it's infinite? It doesn't really cover that case. That's why it's not a perfect definition. Right? Make sure you look at the book's definition for a little bit more careful. Here I am being a little bit more careful. What's the order of an element? The order of little g in capital G is the smallest positive integer n, so that g to the n equals the identity. If no such integer exists, we say little g has infinite order. The symbol that looks like that, again, don't say absolute value of g. That would be even worse, I think. Say the order of g denotes the order. Oh, another typo. Sorry. Oh. Full of typos here. Little g. Okay. Subgroups. This gets a little harder, especially with the subgroup tests. Let G be a group and let H be a subgroup or subset of G if H is a group under the same operation as G. And I really can't quite emphasize that enough. Under the operation of G. That is super important to realize. Then we say that H is a subgroup of G, and we write, don't say less than or equal to. Say H is a subgroup of G. Here's an illustration why the operation must be the same. It is super important. You might say, hey, isn't Z4 a subset of Z5? And they're both groups. So shouldn't Z4 be a subgroup of Z5? No, no, no. Pretend I never wrote that. The operation is different. Mod 4 addition in Z4 and mod 5 in Z5. Z4 is not a subgroup of Z5. Likewise, it's not a subgroup of Z6 or Z7 or Z8, etc. It's not a subgroup of Z, the integers themselves, because you don't do any modding for the addition in Z. Okay, that's the first thing to realize. Think about that kind of example. Very important. If H is a subgroup of G that does not actually equal G itself, then you call H a proper subgroup, and you can write this without the equal sign. Though, technically speaking, when you're talking verbally with somebody here, you should say H is a proper subgroup of G when you see the symbolism. Just like you can say 5 is less than or equal to 5. Just like you can say 4 is less than 5, but it's also less than or equal to 5. I could write the less than or equal to symbol here, but don't say less than or equal to. I can do that because I'm telling you about it right away. I'm telling you to avoid saying those things. Just like I can say 4 is less than 5, and also 4 is less than or equal to 5. If H is a proper subgroup of G, I can use this symbol instead if I want. But if I want to emphasize that it's a proper subgroup, then use that symbol. Every group is its own subgroup, and it also has the trivial subgroup, the subgroup consisting of just the identity element. So the subset is subgroup. The subset just consisting of the identity element is a subgroup. It's called the trivial subgroup of G. A subgroup that is not just the identity is called a non-trivial subgroup of G. Is it really a subgroup? Well, yes. E multiplied times itself any number of times is E. It's its own identity, it's its own inverse, it's closed under the group operation, the associated property so works. The trivial subgroup is indeed a subgroup. Note, this is a pretty obvious thing. If H is a subgroup of G and K is a subgroup of H, then in fact K must be a subgroup of G. We are talking the same operations, so this follows just from set inclusions. Here's G. H is a subset of G. It's also a subgroup of G. K must be a subgroup of H because you're assuming must be a subset of H because you're assuming it's a subgroup. And therefore, K is a subset of G. And it also is a subgroup because the operation is assumed to be the same here in this notation. So that's a pretty obvious thing, and you can use it whenever you need to. There are subgroup tests. Just like in linear algebra, there was a subspace test. Talk about more linear algebra analogies as we go here. In fact, well, here's the biggest analogy of them all. Did you know that vector spaces are groups? Under addition, if you ignore the scalar multiplication. Right? There's two operations in a vector space, addition and scalar multiplication. You got the axioms. If you ignore scalar multiplication, you only focus on addition, vector spaces are groups with respect to that addition. In fact, they're abelian groups. Commutative property holds. Something called the one-step subgroup test. Let G be a group and let H be a non-empty subset of G. Then H is a subgroup of G whenever the following implication holds. What is that implication? That implication is A and B, assuming to be an H, implies that A, B inverse is an H. Let's do this with a simple example. Let's consider Z6 under addition mod 6. There are the elements of Z6. Operation is addition mod 6. What's an example of a subgroup of this? Are there any besides the trivial and non-proper one? There are, for example, that set under addition mod 6 is a subgroup. It's got an identity, 0. Every element has an inverse. 3 is its own inverse. 3 plus 3 is 0 mod 6. And it's closed. 0 plus 0 is 0. 0 plus 3 is 3. 3 plus 3 is 0. Given any two elements like 0 and 3 that are in H, is this true? Well, remember the addition, the operation over here is addition, so I have to switch to additive notation. I really want to know, is A minus B in H? In other words, is 0 plus the additive inverse of 3 in H? But 3 is its own additive inverse. 3 plus 3 is 0 mod 6. Negative 3 is 3. And that is an H. If A and B are both 3, then A minus B is 3 minus 3. 3 plus negative 3 is 0. 3 plus 3 is 0. Do you get this? When you say subtract, what you really mean is add the additive inverse. But what is the additive inverse of negative 3 mod 6? It's 3. 3 is its own inverse. Let's make it a little harder. That's not a full proof, by the way. Here's another subgroup. 0, 2, and 4. Let's take A equal to 2 and B equal to 4. Is A minus B in the subgroup? Is 2 minus 4, which really means 2 plus the additive inverse of 4 in H. But what is the additive inverse of 4? What's the additive inverse of 4 in Z6? 2, right? Because 2 plus 4 gives you 0 mod 6. 0 is the identity. This is the same as 2 plus 2, which is 4, which is NH. Four minus 2 is the same as 4 plus the additive inverse of 2, which is the same as 4 plus 4. The additive inverse of 2 is 4. And 4 plus 4 mod 6 is 2. Again, you show your parents this kind of stuff. They're like, what? You're a math major? What are they teaching you? 4 plus 4 equals 2? In Z6. After quiz, we will look at abstract applications of this. Let's take a quiz.